Hello everybody. In this video, we are going to be dealing with optimization. Now, this is one of the most hated topics by most students. I'll understand why, but let's actually try and make this very simple, okay? So with optimization, it's usually when we have to deal with different shapes, but we have to find a way to maximize or minimize some area or volume. So maximizing will usually take place if you have to deal with area and volume, and minimizing usually takes place when you have to deal with perimeter and surface area, since they are the lower parts of each, right? It depends on the units in that case, right? Because you know that area and volume, they dominate in terms of units over there, perimeter and surface area, respectively. So what does this mean by if fixed perimeter? So I try to simplify this in a very simple way. If you have a fixed perimeter, meaning they give you a perimeter, right? So usually they'll give you maybe like volume, or they'll give you surface area, or they'll give you something, right? They'll give you some value of, maybe they'll give you the volume. For example, it might be 30 cubic centimeters. And then that means that you will need to, because they gave you a fixed volume, minimize the surface area, meaning you're going to have to differentiate the surface area. So you're going to have to write the surface area as a function. However, you're going to need to know, you have to remember the formula for them. That is why students hate this, because there's so much formula. But most of the times you don't really have to memorize them. You can actually just intuitively get them based off of the dimensions. So let's look at this. If you have a fixed perimeter, then you'll maximize the area, and then that means we are differentiating the area, meaning this is what we are going to differentiate, okay? So you should know how to differentiate from now on, after the videos that you've seen earlier. So we have the next one, which is if we have a fixed area, we'll minimize the perimeter, meaning we're going to differentiate the perimeter. So perimeter is going to be the function. So this is obviously, the first two is obviously for two-dimensional, and then the last two is for three-dimensional. If we have a fixed surface area, then we're going to maximize the volume, meaning differentiate the volume. And like I said earlier, if we have a fixed volume, we're going to minimize surface area, which means we're going to differentiate surface area. So if you're still a little bit lost, let's get into an example, and then we'll actually explain what is going on. Alright, so here's our first example. We're going to start off with something three-dimensional. Just note that even though it is three-dimensional, that doesn't necessarily mean it's a more challenging question, because sometimes there are also two-dimensional problems which are much more challenging than three-dimensional, okay? So we'll do more of the more calm versions of this, okay? So here we want to construct a cylindrical can with a bottom but no top that will have a volume of 30 cubic centimeters. Now we need to determine the dimensions of the can that will minimize the amount of material needed to construct the can, okay? So first things first, we're going to construct a cylinder, okay? And it says it says a bottom but no top, and they give us the volume. So what does that mean? That means that our volume is fixed, okay? So first things first, we know that volume is fixed, meaning when volume is fixed, that means we are going to differentiate the surface area, okay? Surface area is going to be our, what we are going to minimize, because it's the least dominant over volume in terms of unit measurement and dimensions, I guess. So just remember that you're going to minimize the one with the least dimensions in the problem that you are given. So if it's a three-dimensional problem, you minimize the one with the least dimension. If it's a two-dimensional, same applies for that one, okay? So for this one, this is what we call a constraint, okay? So our constraint is going to be the fixed volume, okay? And what is the volume of a cylindrical can? So let's say, for example, you didn't remember the formula. You came into the examination and you just realized, oh crap, I don't know that formula. Well, lucky for you, you don't really need to remember it. You just need to go based off of the shapes, right? So let's look at it this way. We need to draw our cylinder. Let me just draw a cylinder here. Not a very perfect cylinder that I'm going to be doing, but we're going to do a nice cylinder over here. Okay, let me make it at least appealing to the eyes, because I know with my drawings it's always terrible. okay? And then we are going to have no top, by the way. So that's what the question said. Cool. So here's our cylinder. Very nice looking cylinder. And we said we want to construct one that has the bottom, okay? So it does have a bottom, so we're going to shade the bottom. And then it has no top, so which means we are going to exclude the top, okay? So we'll do it by an X, and then we'll just shade the rest of the cylinder, okay? Now remember that a cylinder contains something called the height, and also it contains a circle. And notice that we need to multiply the height by the area of a circle in order to get the volume, okay? Because remember that the area of a circle is just going to be two-dimensional, or what am I saying? Sorry. An area of a circle is going to be the second. It's a square. It's a square unit, right? Meaning, if we multiply a square unit by just some height, which is not square, it's to the power of 1, then notice we are just going to get a cubic units, okay? So notice that this circle over here is going to be pi r squared, okay? I'm sure you should remember the area of a circle though. So we need to multiply them to get the volume of the cylinder, okay? So the constraint would be the volume is equal to pi r squared times h. Okay, there we go. Cool. And what we are going to minimize is the following formula for the surface area, right? So minimize. Now, how are we going to get the formula for the surface area, okay? So this is how we're going to get it. All we are going to do is break up the dimensions of the cylinder as follows, okay? So notice that the cylinder contains two circles and some curved rectangle, okay? In this case over here, you can see that the rectangle is here, but it's actually kind of like curved a little bit. So right now, we need to break it up. Since it doesn't have a top, we are only going to include the bottom circle. So here we're going to draw the circle, okay? And remember that the surface area is essentially the sum of all the dimensions within a three-dimensional object, okay? So we're going to add all the dimensions. So if there was two circles, then we would have 2 times the area of the circle. However, we only have one circle where the area here is pi r squared, and we're going to add that with the area of the rectangle that we have, right? The rectangle obviously looks something like this, okay? And what you notice is that it goes along, let me do it a little bit bigger. So it kind of is curved a little bit here. So we know that this dimension is the height, okay, the vertical distance or the vertical dimension. And then we can see here that this little perimeter over here is just the perimeter of a circle, right? So therefore, and remember that this thing actually wraps around to form a full cylinder. So we know that the top dimension and bottom would be 2 pi times radius, which is the perimeter of a circle. And if we multiply that together, then we get the total area of 2 pi r times h. So therefore, we're going to add those areas together, and then what we're going to have is the surface area to be pi r squared plus 2 pi r times h. And notice if we had the extra circle, it would have been 2 pi r squared because it's two circles, and the 2 would have fallen there. That's probably what you would have seen in your formula sheet. However, we are manipulating a little bit here. Okay, now let's get into the actual problem solving for this question. Okay, so for this next step, I need to listen very carefully. You see this constraint over here? We are going to use this constraint to form the surface area into a function in terms of one variable alone, okay? Now, what we can do is we need to use the constraint. We need to make one of these variables the subject of the formula. And why am I saying that? Because notice that we were given the volume, okay? So first things first, we were given the volume. The volume is equal to 30 centimeters cubed. It was given to us, right? So then this further implies to us that we can substitute 30 into the formula of the constraint, which is the volume formula. Therefore, 30 is equal to pi r squared h, okay? So my question to you is, which variable would be easier to make the subject of the formula? Well, clearly, if we let h be the subject of the formula, it would be easier, so you don't have to deal with square roots when you are square rooting both sides. So therefore, we'll let h be the subject of the formula, so we'll divide both sides by pi r squared. Then we are just left with h is equal to 30 divided by pi r squared, okay? And there we go. We'll just label this equation number 1. And then notice that we can just substitute h into the formula of surface area. So remember what I said? We need to make sure that surface area is a function of one variable. So we need to manipulate the constraint that we have to make one of the variables the subject of the formula to plug into the surface area. Because remember, these are the dimensions within the same object. So there can't be different dimensions within the same object, obviously. So that's why this thing works. So now we're going to tell the examiner we are going to sub equation 1 into the surface area. Okay? We're going to sub 1 into SA. And then from here, we are going to do the following. We're going to see that the surface area is now going to be equal to, what was it initially equal to? It was pi r squared plus 2 pi r h. So pi r squared plus 2 pi r. And notice that we are going to replace h with 30 over pi r squared. Okay. Cool. Now from here, we're just going to keep simplifying. Okay. SA is equal to pi r squared plus, and then notice here that the pi can cancel with this pi, and then r can cancel with one of the r's here, so we're left with r in the bottom. So then therefore we are left with 2 multiplied by 30 over r. Okay. And because we want to take the derivative of this function here, okay, we can just get it derived ready as well, which this is going to be pi r squared plus 2 times 30, which is just 60. And remember, r we need to write as a negative exponent. When we're differentiating, no variable can be at the bottom. It has to be a part of the original equation like this. So we write it as a negative exponent. Cool. Something you can notice is we can also rewrite SA as SA of the is a function of r. Okay. Because we actually, this is what the whole purpose was. We wanted to rewrite it as a function of r so that we can differentiate it fully. Okay. So then the next step is to take the derivative on both sides so that we have SA prime of r. Write that apostrophe a bit better. There we go. And then the derivative of pi r squared with respect to r is just going to be 2 pi r. Notice that the derivative of the area just gives us the perimeter. And then here we're going to add it with, or I guess not really add, because remember the power rule for different derivatives. Yeah, the power rule for derivatives, I almost said integrals, is when we multiply the coefficient by this negative 1. So it'll be minus 60 times r. Then we're going to minus the exponent by 1. So it's negative 2. Okay. Cool. Now remember that optimization is just an application of maximum and minimum, meaning this is where we let the first derivative be equal to 0. Why? Because when we let the first derivative equal to 0, it is essentially us saying that the tangent line is equal to 0, meaning it is a straight line, which is an indication that there's either a maximum or a minimum on the function. That is when the gradient is always 0, is when there is a maximum or a minimum on some function. Okay. Usually the polynomial functions after the second degree. At the first degree and then after, obviously. Okay, cool. So we are going to tell the examinator to let SA prime of r equal to 0 such that what we're going to do is we're going to say 0 is equal to 2 pi r minus 60 times r to the negative 2. And then from here, all we are going to do is we need to get rid of this r to the negative 2. Okay, so we can multiply, or I guess before we multiply both sides first, let's take the thing over. So we have 2 pi r is equal to positive 60 r to the negative 2. Okay, and then from here, we can multiply both sides by r to the power of 2, so that we can actually get rid of this exponent here. Okay, so then we are left with 2 pi r to the power of 3 is equal to 60. Okay, so just note that I multiply r to the power of 2 on both sides. Okay, cool. Just in case someone gets confused. And we need to actually solve for r, because remember, what was the actual question? The question said, determine the dimensions of the can that will minimize the amount of material needed to construct the can. So we need to find the dimensions, meaning we need to find the value of h and r. So r, we can determine first here. We can just solve for r here. Take 2 pi over, so then we're going to have r cubed is equal to 60 divided by 2 pi. And then from here, we can cube root both sides. So that what we'll have is r on its own. And then we are just going to have the cube root of 60 divided by 2 can be simplified as 30. We have 30 over pi. Okay, cool. So there we go. We found one of the dimensions. So since we found the one dimension, we can now find the other dimension by substituting r into h. Okay, and h is equal to 30 over pi r squared. Meaning it'll be 30 divided by pi r squared, which r is just equal to the cube root of 30 over pi. And this is all squared. Okay, and you can simplify this further if you want to, which probably is recommended, but otherwise this is still one's entire value. Okay, this should actually give you the exact same value as that, by the way, according to what I've done. So the real question is, how do we conclude this? You'll say, therefore, let me write this a little bit to the side, therefore, the minimizing, well, you know what, let's type this out. Let's do everyone a favor and type it out here. So you can say, therefore, the minimizing dimensions of the open can will be where, and now zoom out as well because I'm not writing. It will be where r is equal to, and then I will keep that blank for now, and h is equal to, and we'll just write down those values, okay? So r was equal to what? The cube root of, let's write all the way this side now, it's crazy. The cube root of 30 divided by pi, okay? And then h was equal to all of this. So all you need to do, select it on your paper, and then hit copy and paste, and then you should have it here. Cool. So there we go. It was not that difficult. There are steps to this, so let's quickly go through the steps one more time, and then we go to the last question that we're going to do, which is a two-dimensional problem. So like we did, the constraint is basically based off of the fixed value that they give us, and then we use the volume as a constraint in this case. Then we want to minimize, I almost said South Africa, we need to minimize the surface area, which is our function. We need to write it in terms of a function of one variable. So we use our constraint, and then we solve for one of the variables, and then plug it into the surface area, so that we get it as a surface area is a function of one of the variables. You could have said h, but it would have taken longer. Then all you do, because it's an application of max and min, we're going to find the derivative on both sides. Then we're going to let the derivative be equal to 0 to find the minimum dimension for r. And then we solve for r, and then we plug r back into h, our equation 1, and then therefore the minimizing dimensions of the open can will be where r is equal to that and h is equal to all that. Okay, and then full stop. Cool. Let's go to the last question. Alright, so here's example number 2, our last one. We are going to fence in a rectangular field and have 200 meters of material to construct the fence. Determine the dimensions of the field that will enclose the maximum area. Okay, so first things first, let's understand something. We need to fence in a rectangular field and have 200 meters of material to construct the fence. Meaning, we note that this must be two-dimensional, okay? Because we need to deal with 4 different dimensions. Actually, 2 different dimensions, I guess, but 4 sides, obviously. Because remember, there's an X and a Y dimension, in this case over here, of a rectangle. Okay, so that's something that we should know. So let's actually just draw a diagram of what we have. So let me just draw a rectangle quickly. So let's say, for example, we have a rectangle that looks something like this. It doesn't have to be exactly what they want or whatever. They didn't even tell us what type of rectangle they want. However, we just need to know it's a rectangle, meaning that opposite sides are obviously equal in length, in this case over here. So we note that we have one side, let's call this side let's call it the width, okay? Which means this dimension is also going to be the width, and let's call this the length, okay? So there we go. We know that the total amount of material that's covered is 200 meters, okay? Meaning that the sum of each and every single side must be equal to 200 meters, which gives us the perimeter, right? So our constraint comes from the information that we're given, the fixed perimeter, okay? And what did we say? We said in the beginning that a fixed perimeter, we need to maximize the area. Isn't that what we're doing in this question? So meaning, we need to do the following. We need to take L plus W plus L plus W. We need to add all the sides and equate it to 200 meters. And then we can just obviously simplify it from here. Notice it's going to be 2L plus 2W is equal to 200. We can skip the M for now, okay? And then, for a moment I was very convinced that that Venom was taking over my PC right now. So anyway, we need to take out a common factor of 2, or we can just divide both sides by 2, so that we have L plus W equals to 100. You don't really need to do this, but it's just simpler this way, and yeah, it's pretty easy. And remember in the last question, we wanted to let one variable be the subject of the formula to make sure that our volume is not volume. Well, I guess in the last problem it was volume, but we need to cover our area, okay? We can deal with that soon. But for now, let's work with what we need to maximize, okay? So we need to maximize the area. And the area of a rectangle is basically going to be length times width, okay? So there we go. Now that we got that out of the way, we need to look at the constraint in this case over here, okay? So which one do you want to make the subject of the formula? L or W? For this one, let's make L the subject of the formula. It really doesn't matter as long as you make one of them the subject and then you find both of them. Okay, so now what we are going to do is the following. We are going to have L is equal to 100 minus W, and then all we are going to do is label this equation 1. And then what we're going to tell the people is, well, I guess wrong symbol. We're going to tell them we are going to sub 1 into the area, okay, such that with this information that we have, we are going to reduce the amount of variables from 2 to 1, okay? Because notice that we have L times W. And then the area is going to be what? 100 minus W multiplied by W. And then we can multiply the W in. Then we have area is equal to 100 W minus W squared. So what we need to do now is maximize the area, okay? So obviously for this one, we need to differentiate both sides, and we know that it's actually a function of W. So we can clearly rewrite this as A of W. So therefore, when we take the derivative on both sides, we are left with this. It's going to be W is equal to, and then the derivative of 100W with respect to W is just going to be 100, okay? Because we're going to notice that this variable, since it's to the power of 1, it will become 0, so we'll just be left with a constant. Then we'll minus it by 2W, because the derivative of W squared with respect to W is just 2W, okay? And then remember, we need to maximize it, okay? meaning let it be equal to 0. So we are going to tell the person here, let a prime of w be equal to 0, such that what we're going to actually have now is 0 is equal to 100 minus 2w. Okay, so this is small w's, so we change them. And then we just solve for w, right? So from here, we're just going to have 2w is equal to 100. And then therefore w, if we divide both sides by 2, is going to be 50. Okay, and w, remember what units it is? It's in meters. You always have to make sure you have the meters right at the end. Now all we need to do is we need to determine what is going to be the length. Okay, so right now we have the width, but now we need to find the length, meaning we need to substitute this in here. So all we're going to do is we are going to say here that length is just equal to 100 minus the w, right? And w we know is equal to 50. So therefore, our L is just going to be equal to 50 meters as well. Okay. Now remember what the whole point of this question was. We need to determine the dimensions of the field that will enclose the maximum area. So what we can actually do for this one is we can find out the maximized area, but before we do that, let's actually see whether or not it is a maximum, because sometimes in a question you may be asked to prove that it is indeed a maximum or minimum, or sorry, prove whether we are maximizing or minimizing. And how do we do that? We use the second derivative. And how do we actually show that? Well, think about it this way. When we're finding out if there's a maximum or minimum for a parabola, we need to know the concavity. We need to know the shape of the concave. If it's concave up, it'll have a minimum. If it's concave down, it'll have a maximum. Okay? So let's do a second derivative test for this one. And I'll do it in red. So this is to show, this is to show if it is max or min, right? Just to verify our answer, to see whether it is maximizing or minimizing. It should be max though, okay? And if it is max, that means the second derivative should be less than 0. So let's take the derivative of this. So it'll be a double prime of w, which is equal to, the derivative of 100 is just 0, and the derivative of negative 2w is just negative 2. And notice that this value implies to us that a double prime of w is actually less than 0, because it's negative, which implies to us that this is concave down. And when there's a concave down, we have a maximum. Why is it maximum? Because the shape is going to look something like this, where it has a maximum. So therefore, it is indeed maximizing. So we can find the maximizing area. We can conclude over here. Therefore, the dimensions, we're going to write it down. I'm just going to write it down. So here we go. Therefore, the dimensions that maximize the enclosed area, maximize the enclosed area of, what is the enclosed area? Well, it's just going to be the area of 50 multiplied by 50. But remember, the length is going to be length of 50 meters and the width of 50 meters. And if you multiply them together, you're going to get 2,500 square meters. Okay, and there we go. That is optimization. It is not that difficult. There are steps to this. So once again, we'll look at the steps. So for the 2-dimension, notice that we were given a fixed perimeter, which is 200 meters, and then we use the constraint to be the perimeter formula for a rectangle. And then all we need to do is just maximize the area. And then notice that we'll just make the subject of the formula for the constraint to plug into the area, then we differentiate it and let it be equal to 0, so that we can see where it maximizes. And we note that it maximizes when the dimension W is 50 meters, and when we substitute that into L, it's also 50 meters. And we proved that it was maximizing by taking the second derivative of the area to see whether it was negative or positive. Because it was negative, it's concave down, and then that means it's a maximum, as shown here. And then that is our conclusion.